All right, the next section is 15.3 triple integrals. So in this section, we're just basically extending what we already know about double integrals and taking it that extra step, as is usually the case in math. So the first thing we're going to do is revisit the Fubini's theorem. We should remember that in 15.2, when we did double integrals, 15.1 and 15.2, that if you integrate over a rectangle, then you can just break up your triple integral over the set of bounds. Well, for a rectangle, we only had a change in x and y. So a range for x, a range for y. Well, in 3D, if we have a rectangular prism, so a box, then we really have a range for x, y, and z. So this is just the one-dimensional higher analog to what we've already done. So if we take a look here, example 1, evaluate this triple integral x squared e to the y plus 3z dv over the box B, where, again, this is our range for x, y, and z. Then we can just set this up as the following. The integral from 1 to 4, integral 0 to 3, integral from 2 to 6. X squared e to the y plus 3z, and this would be in the order dz dy dx, because if we look, 1 to 4, that's the range for x. 0 to 3, that's the range for y, and 2 to 6, that's the range for z. We can take it another step further because this expression, e to the y plus 3z, is really just e to the y times e to the 3z. And because all of our bounds are constants, we can actually split this up into an x integral times a y integral times a z integral. Then each of these can be integrated as is. So we'd have 1/3 x cubed between 1 and 4. Then the y integral is e to the y between 0 and 3. And the z integral is 1/3 e to the 3z between 2 and 6. And if you evaluate all those, you will get the monstrosity that is 7 times e cubed minus 1 e to the 18 minus e to the 6. Just evaluating all of those. Each one of these is a Calc 1 integral, so fairly accessible.